Okay, so I think that we can start. Thank you very much, everyone, for joining this lecture 21 about graphics processing units corresponding to this digital design and computer architecture course. Today, I'm giving this lecture because Professor Mutlu, unfortunately, cannot do it himself. My name is Juan Gomez Luna, and I'm one of the TAs. Before we start with the materials, let me remind you that there is an extra assignment in our website about Amdahl's law, about this paper from Jean Amdahl, and you can get to 1% extra credit for this assignment. Recall that the deadline is on June 15th. So we strongly recommend you to use our guidelines on how to review the papers analytically. Here you have some links in the slide and also some example reviews. So let's very quickly recap what are different things that we have covered in this course. We started with the microarchitectures like the single cycle and the multi-cycle microarchitectures. Then we visited pipelining and the different issues with pipelining, and then out of order execution. After these paradigms or execution techniques applied to CPUs, we have seen also other execution paradigms. For example, fine-grained multi-threading or superscalar execution, systolic arrays, and now we are covering SIMD processors. In this lecture, we are going to first finish with SIMD processors, a lecture that you started last Friday, and then we are going to cover GPUs. Let me also remind you what are the required readings for this week. The required reading is the NVIDIA, and I strongly recommend is the paper about MMX extensions in Intel architecture. We are actually going to talk about these MMX extensions today. Okay, let's very quickly recap on SIMD processors. SIMD processors and also GPUs by extension, because they are kind of specialized or improved SIMD processors, are very good at exploiting data parallelism. In particular, they're especially good at exploiting regular data parallelism. And we say that it's regular when all the different processing elements that we have in a SIMD functional unit with the same instruction. That's why we call this paradigm or this class of computer, according to Flynn's taxonomy, SIMD, single operation or single instruction on multiple data elements. This is one of the 4 classes of computers, according to Flynn's taxonomy. Among these SIMD processors, seeing in the course 2 main ones, 2 main types of SIMD processors, which are array and vector processors. And let's recap what's the difference between them. In an array processor, we have one instruction operating on multiple data and executing on different processing elements, on different spaces. On a vector processor, have the single instruction execute multiple data in consecutive time steps, the same space. I think it's very clear this slide. The array processor, there are some elements, all of them can execute different types of instructions like load, add, multiply, etc. We have the same operation at the same time on different processing elements, and we have different operations in the same space, in the same processing element. While in the vector processor, we typically have kind of specialized processing elements for load, add, multiply, etc. And here we execute the same operation in the same space, that is in the same processing element, while different operations at the same time in different processing elements. Recall also that these vector processors need to access data, and the way of accessing data is going to memory. And there in memory, if we really want to be able to access in parallel, we need to have a memory that allows us to do so. In order to do that, we divide the memory to independent banks that can be accessed independently. And this way we are able to sustain as many concurrent accesses to memory as banks we have. Recall also how vector instructions are executed on the pipeline of these processing elements that compose either array processors or vector processors. We can have a very simple SIMD processor with a single SIMD unit like this one in the figure, where we will have to run one by one, execute one by one the different operations that this vector addition contains. We can have several of these ALUs, and this way we can also execute concurrently in the space. We usually group these functional units that compose a whole SIMD engine or whole SIMD functional units. We group them into what we call lanes. Each of these lanes is typically composed by different several of these ALUs, and they have access to a certain amount as they are needed for the execution of the operations in these ALUs. We talk about a whole register file that is partitioned, and each of the partition is assigned to one lane. Here you have another view of how SIMD instructions are executed on the SIMD pipeline. In this particular example, we consider a vector length of 32. So we have 32 elements inside each vector and inside each vector register, but we only have 8 lanes. So if we want to execute, for example, this load instruction using these 8 lanes, we'll have to issue 8 operations every cycle, and we will need 4 to issue the whole vector of 32 elements. And this is for the load operation, and then we may have a multiply operation on a different unit, an addition, and then another load, multiplication, and addition. And observe the big advantage that we have here in SIMD processors is that all of these operations that you can see here represented by these small colored icons, in total 24, are executing at the same time in the same cycle. So that's the big advantage, the ability to exploit regular data parallelism. But there are also disadvantages. As you may remember this slide, it's difficult, it's hard for a programmer to be able to pack the data in the necessary way to use SIMD instructions and to use these SIMD engines efficiently. Luckily, over time, compilers have improved and they have managed ways of generating vectorized code automatically. So recall this example. It's a very simple code, like a vector addition. We have a for loop. We go over 2 arrays, B, and a third array, which is the output array C, composed of n elements. And in each iteration of the loop, we read 1 element from A, we read 1 element from B, we add them, and we store the result in C. In total here, we have n iterations, right? And the way that these iterations are going to execute on a regular single-threaded CPU or single-core CPU is something like this. We will first load an element of A or element 0 of A, then element 0 of B, then we add them, and then we store in C0, right? And then we go to iteration 1. Iteration 2. So the good thing here is that there are a lot of independent instructions. So we can execute what we call instruction level parallelism. For example, this addition here is completely independent of this addition here. So they can execute in parallel. And this is something that the compiler can realize, and based on that, generate vectorized code. Something like this. The compiler can identify what instructions can be packed together. This load here will be part of a vector load instruction, and then another vector load instruction, and then a vector add, and then vector store. So this way we can create code automatically and efficiently. Important issue here is that we obviously require extensive loop dependence analysis. The compiler should be able to realize by itself that all these iterations are independent and then generate the vectorized code. So in order to summarize about vector or SIMD or array processors. They are very good at exploiting regular data level parallelism. They perform the same operation on multiple data elements. Clearly, we can improve performance because we can execute operations in parallel, instructions in parallel. However, this performance improvement is limited by the vectorizability of the code. It's limited by how much parallel code parallel sections we really have in the code. This is why, and this is something that Amdahl himself realized, even though he was the inventor and developer of one of the first supercomputers, Cray-1, which was composed by hundreds of parallel execution units that could execute SIMD instructions. He was also conscious about the importance of a fast execution of the non-parallelizable code, the sequential code. That's why Cray-1 was also not only the fastest machine, but also the fastest sequential or scalar machine of its time. Today, we still have many SIMD operations in many different systems like Intel, IEDM, PowerPC, ARM, etc. We are going to talk about a couple of examples today. Recall Amdahl's law, the speed up that we can get in a program where there is some parallelism depends on what's the parallelizable fraction of the program, because this is the only part of the program that we can really speed up by using the whatever number of processors we have. Yeah, this is the paper that, as you know, is suggested reading, an extra assignment, and that you can submit until June 15. And here are some links to the guidelines. This is the beginning of the paper. And if you want more, to know more about parallelism and heterogeneous execution programs with parallel parts and sequential parts, you can watch this lecture by Professor Mutlu from the Computer Architecture Master's. It's lecture 16B. Here you have another one that analyzes more in detail sequential bottlenecks, in this case, multiprocessors. And this one is about bottleneck acceleration. What can I do to accelerate the bottlenecks in these codes that, okay, they are great because they have some part of the code that is parallelizable and I execute it, for example, using SIMD operations, but some other is inherently sequential, not too much. I cannot parallelize. There are also ways of speeding up, for example, these critical sections, which are sections of code that where only a single thread can be executing at the same time. There is no possible concurrency. Here you have the links to these lectures. So we will very soon finish SIMD operations, processors, but now we are going to see a couple of examples of SIMD operations in modern processors and in modern ISAs. The very first one are all the SIMD applications that we can find in, for example, x86 processors or ARM processors as well. The idea of including SIMD extensions, kind of SIMD functional units inside these general purpose CPUs came from I would say 80s or 90s, when multimedia applications start being more and more used and more important. At that point, vendors realized that these applications could greatly benefit from the use of SIMD extensions. Essentially, the idea is that multimedia applications like audio, video, graphics, or games, they have a lot of parallelism. For example, in video or in graphics, what we need to generate are images composed by pixels. And it's very typical that the computation that we apply on these pixels is the same. So there is a lot of regularity there, a lot of regular data parallelism that we can exploit. One additional consideration here is that we may not need to use like very highly precise data values. We may not need to use 64-bit or 32-bit per pixel. We typically use much smaller representations, like a single byte per pixel, or maybe several bytes if we have a color image and each of the bytes represents one channel of the image. So the idea here is that we can modify the ALUs that we already have in the system for 32-bit operations, and we can operate on several bytes or at least several smaller data types at the same time. Here in the figure, you can see a this will be like a 32-bit adder, where we are going to add all the bits, all these elements in this register to the elements in this other register. The only modification, or the main modification, that we need to do in the ALU is eliminating the carry from bit 7 to bit 8, or from bit 15 to bit 16. And in this way, we'll be able to perform an here, an independent addition here, and an independent addition here, and so on. Okay, so this is like the key idea that SIMD extensions on general purpose CPUs are based on. Let's take a closer look at the Intel Pentium MMX operations as an example of this SIMD extension. So the thing is that if you have, for example, a 64-bit adder or ALU, you can operate on 64-bit elements, or you can operate on 2 32-bit elements at once, or 4 16-bit elements, or 8 bytes, right? Let's see, because recall, we have said before, it was difficult, it was a challenging program using SIMD operations, right, or SIMD instructions. We are going to see now an example of MMX, how to use MMX instructions. This is a multimedia, let's say, task that can be parallelized using the SIMD extension, the SIMD MMX extension in an Intel CPU. So this example essentially consists of a main image where we have a woman, and this woman is at the front of a background. This is what we call the chroma keying. And here, the processing that we want to apply to this image is replacing the blue background with some blossom background. This is, for example, you have seen in the TV the weather forecasting, right, where the weatherman or the weatherwoman is at the front of the weather map. So this is the kind of technique that is used there. So that's what we are going to do here. In this case, we have a map of Switzerland behind. What we are going to have is a blossom background. The computation that we need to perform here in reality is very, very simple. If you write the sequential code, it's as simple as going through the whole image, pixel by pixel. And in this image, if one particular pixel is blue, we are going to replace it with the corresponding pixel in the same position in this Y image. If it's not blue, then we will directly copy to the new image. So in order to do this on a SIMD processor or using SIMD MMX extensions, well, the first thing that we have to do is to create a mask. The idea is that for every pixel of the image, the X image, we are going to check whether it's blue or not. And to do so, we compare each of the individual pixels that we will load into these vector registers, this, for example, vector register MM3. We compare all the individual bytes here with the a vector register MM1 that contains blue in every single byte, right? So using this operation here, this instruction, which means packed, compare, and well byte, we compare one by one, and the output will contain zeros or one. And this is our bit mask that we are going to use in the subsequent computation. So once we have the bit mask, let's see what we have to do with the blossom image and with the woman's image. Let's start with the blossom image. Recall that this is the computation that we have to perform on a sequential processor. Here in the SIMD processor, we are using the mask. Thing to do is to load chunks of the blossom image into a register, in this case MM4, and then we apply the mask. And the way that we apply the mask, remember that this mask has some bytes that are zeros, some bytes that are one, by using P and, packed and. So what we do is element-wise, we do an AND operation between a pixel of the blossom image and the corresponding position of the bit mask. So this is what we finally have in register MM4. And Then we have to do the corresponding computation for image X, the woman's image. So here, again, we are going to use the mask. And here in MM3, we are going to load of pixels of the image from of the woman. Some of these pixels are blue, some others are the woman herself. And now what we do is again applying the mask, but observe that this instruction is different. It's not P and, it's P and not. This means that we first flip this mask and then we perform the AND. So these zeros will be 1, and then we do the AND with these elements here, and then we obtain this output. Pixels from the woman and then zeros. So finally, we do a with MM4 and MM1 as the input operands, and this is the result. This would be the woman at the front of the blossom background. You can see here how you would need to write this code. So let's see another example. SIMD operations in a modern accelerator, in machine learning accelerator. This is kind of optional material for sure. You have seen these Cerebra's wafer scale engine that Professor Mutlu has shown on a previous lecture. It's an amazing computing platform with 400,000 cores in its version of 2019. The new version launched in 2021 has more than twice the number of cores, and it's like, as you can see, compared to the largest GPU, for example, it's like several order of magnitudes more transistors. Let's take a quick look at how these how we can use this wafer scale engine. So this is device, as we already know, is an accelerator for machine learning workloads. And for example, neural networks, as you know, they are composed by multiple layers. So the idea here is that we are going to map these layers onto the different cores, the different tiles of cores that we have inside the wafer scale engine. There might be different ways of mapping these, right? For example, this green layer goes here, the yellow layer goes here, and so on. Here you have like a more detailed example where you can see where exactly each of these convolutional or pooling layers are being mapped onto the wafer scale engine. And also you can see kind of the flow of data that you need to follow, right, in order to be able to follow all the different layers of the neural network. So interesting thing here is that we are using a whole machine, a whole computer. We are dividing it into different pieces, and each of these parts is executing different computations, right? So this is something that we have called before a MIMD machine, MIMD, multiple instructions, multiple data machine. It's, as you know, one of the 4 classes of computers according to Flynn's taxonomy. There is something else here. If let's take a closer look at the wafer scale engine. Here you have a pictorial representation of this wafer scale engine. It's composed by a 2-dimensional organization of 84 dies, and inside each of these dies we have multiple tiles, more than 4,500 tiles, and each of these tiles is something like this. It's like a small core. But let's take a closer look at this small core, because the interesting thing here is that this small core is a SIMD processor again. So yeah, as I was saying, the interesting thing is that each of these small cores that compose this MIMD machine is a SIMD processor. So this is a MIMD machine composed by SIMD processors. Each of these SIMD processors, we know it's SIMD because it has a SIMD functional unit, which is 4-way. So this means that it has 4 lanes, so it can execute 4 operations in parallel. And these operations are the important operations for machine learning, which is the fuse, multiply, accumulate operation. We obviously need some operands to operate using these FMAC SIMD units. To do so, we have some address registers, and using these address registers access a local memory, in total 48 kilobytes of SRAM. Okay, so until now, this is our SIMD processors lecture. Now we're going to start talking about GPUs. But before we start talking about GPUs, I would like to remind you the fine-grained multi-threading paradigm, or fine-grained multi-threading execution, because GPUs, as you already know, are related to SIMD processors, but they also have the ability of execute SIMD operations in a fine-grained multi-threaded manner. Very, very quickly, from a previous lecture by Professor Mutlu, recall the key idea of fine-grained multi-threading. The key idea is that we have multiple hardware threads, multiple thread contexts, each of them with its own PC and with their own registers. And what we do is that every cycle we have a scheduler that takes one instruction from one of these threads and issues the instruction onto the pipeline. The main advantage of doing this is that while we are performing some long latency operations, like for example, going to memory to get some data, we typically spend hundreds of cycles on getting data from the main memory of the computer. Or, for example, while we are waiting for branches to get resolved, we can execute instructions from other threads. So this is the key advantage of fine-grained multi-threading, the ability to hide latencies that fine-grained multi-threaded processors, like for example, hyper-threading that you can find in most Intel processors these days, but also GPUs use. Recall the lecture on fine-grained multi-threading was lecture 14 in this semester. You can also find in this slide another lecture from a previous semester. The contents are essentially the same, but it's explained in a different way. Okay, so now let's start with graphics processing units. We already know that graphics processing units are based on SIMD processors and also based on fine-grained multi-threaded processors. So let's start with the SIMD side of the GPUs. GPUs are SIMD engines underneath. There is an instruction pipeline that operates like a SIMD pipeline. However, there is a main difference here. It is residing in the fact that we don't need to write vectorized code. We don't need to use vector instructions, but we are going to program this GPU using threads. And this is a key advantage from the programming perspective. We can program much more efficiently if we just need to worry on threads individually rather than worrying on packing data on vector instructions and creating bit masks and launching these whole vector instructions onto the hardware, right? We are going to discuss this really thoroughly. And to understand this, we are going to use the same parallelizable code, the vector addition that seen in a previous slide. But before that, we are going to distinguish, or we have to distinguish between two important concepts here. One of them is a software concept, which is the programming model. The other one is a hardware concept, which is the execution model. They are tightly related, but they are not the same. What's the programming model? The programming model refers to how the programmer expresses the code. It's like, how do I, as a programmer, write my code? I may do it in a sequential manner, following von Neumann model. I simply write the sequential code, instruction after instruction. I can write it in a data parallel manner, for example, using SIMD instructions, or I can use multiple threads in a MIMD, or also called SPMD, single program multiple data manner, as we will see. Like, for example, using Java threads or OpenMP threads or P threads, and so on, different libraries like that. And then we have the execution model, is how the hardware executes the code underneath. And for that, we also have different ways of doing that, right? And you already know them. For example, you know that sequential code runs on a CPU, but you also know different types of CPUs. You know in-order CPUs, pipeline CPUs, and you know out-of-order CPUs. They execute the same code in different ways. Some of them are more efficient, some of others are less efficient. Or SIMD code you can execute on a vector processor or on an array processor, or the multi-threaded code you can execute it on a multiprocessor or a multi-threaded, multi-core processor. So the execution model is different from the programming model. And as I was saying in the previous example, we can run sequential code on an out-of-order processor, or we can run SPMD code or MIMD code on a SIMD processor. And that's exactly what GPUs do, as we will see. So now that more or less the difference between programming model and execution model should be clear. One of them, programming model, relates to the software, while the execution model relates to how this software executes on the hardware. We can discuss different ways of exploiting the parallelism, the inherent parallelism that resides in this vector addition here. So remember that this is all sequential code. In a sequential machine, we will first execute iteration 1, then we go to iteration 2, and so on. But there are different ways of exploiting the instruction level parallelism that we have here. We talk about instruction per level parallelism because some of these instructions, or many of these instructions, are independent of each other and they can execute in parallel. Like, for example, this add here is completely independent of this add here. When we express the parallelism that this code has, we can start with the very simple, easiest way, which is just writing sequential code in a CSD. Or we can directly write parallel code using vector instructions in a SIMD manner, or we can use multiple threads, like, for example, OpenMP threads, in order to express this code in a multi-threaded manner. So let's start with this, the first of the programming models, the sequential programming model. We know that a sequential program can be executed, for example, on a pipeline processor, is a way of obtaining some instruction level parallelism, or in an out-of-order processor where the out-of-order processor automatically detects independent instructions and can launch them in consecutive cycles onto the different functional units and have the execution concurrently. In some way, what the out-of-order processor is doing is unrolling the loop, right? Because if you have this iteration and then this iteration, and you somehow can launch this load and this load almost at the same time, and you can have concurrent accesses to memory, what you're doing is unrolling the loop by the hardware. And we can also take advantage of superscalar or very long instruction word execution in order to take advantage of multiple execution units that we may have in our system. So there are multiple ways of exploiting the instruction level parallelism in this sequential code. Another thing that we can do is writing data parallel code, like, for example, in a SIMD manner. We already know that each iteration here is independent. So the programmer or the compiler can generate the SIMD code, the SIMD instructions, to take advantage of this independence of the different iterations, right? The inherent parallelism that we have here. So these two loads and a few more of them until, you know, the maximum vector length that we have is a vector instruction. This will be a vector load. Here we have another vector load. Here we have a vector, and finally a vector store. As you know, where this is best executed is in a SIMD processor like vector or array processors. And yeah, that's something that we have seen in the previous lecture. So now the third programming model is the multi-threaded programming model. In the multi-threaded programming model, the realization is the same. Each iteration is independent. So what I'm going to do is, instead of packing these different iterations in vector arrays and vector instructions, what we are going to do is that each of these iterations is going to be assigned to a thread of execution, right? So this is what we normally do when we write code for MIMD machines. And this programming model is not only MIMD, but also called single program multiple data, because observe that in all these iterations, the program is essentially the same, but they are operating on different data instances. And the good thing, and here is where we bring up GPUs, this SPMD code can be executed on a machine. You will see how we execute this on SIMD engines. In the GPU context, in the GPU world, we talk not about SIMD, we talk about SIMT, because It's the same program and the same instructions for multiple threads of execution that are going to run together on the SIMD units. So in summary, a GPU is a SIMD or SIMD. The main difference with a conventional SIMD processor is that we don't program it using SIMD instructions, we program it using threads, following an STMD programming model. Each thread executes the same code, the same program, but operates on a different piece of data. And because we are using threads, each thread has its own context. Each thread, in principle, can have its own PC, can have its own registers, and so on. So here is where the, let's say, the advantage of using this programming model comes from the perspective. We can handle the different threads in a completely independent manner. We just assume that they are going to run independently from others, even though that's not the truth that's not the truth on the hardware, but that makes the life of the programmer and also the compiler easier, because you don't really have to worry about packing the data elements in the right way on a vector register and write the code using the vector registers, which is quite more challenging. The thing is that what the hardware is going to do with these threads is that automatically or dynamically, this hardware is going to take these threads and is going to create groups of or sets of threads that we call warps or waveforms. And these are the, let's say, SIMD units that are executed all together onto the hardware. We are going to take a closer look at this. So a warp, for a easy definition, is essentially a SIMD operation formed by the hardware dynamically and transparently to the programmer, who only needs to worry about writing code for individual threads. So going again to the slide of the parallelizable code, it's a single program, multiple data program, what we are going to use. And this program is going to be executed by warps, which are sets of threads that execute the same instruction. So in some way, this warp is the SIMD unit and is the entity that is executing the SIMD instructions. So for example, here, these two loads are going to be part of the same SIMD instruction that is going to be executed by warp 0. This instruction is, for example, stored in PCX, and then we have the next instruction for warp 0 is in PCX plus 1, and this addition PCX plus 2, and this store is PCX plus 3. And interestingly here, we will see we can interleave the execution of these instructions for warp 0 with the execution of the same instructions for other warps, because in our program we will have not a few threads that are going to be executed as a single warp. We will end up having hundreds or thousands of warps, as we will see. Okay. So graphics processing units is SIMD not exposed to the program. It is a SIMD execution model. In the conventional SIMD, what we have is a sequential execution stream of SIMD instructions. So in reality, we have a single thread, and this thread is execute vector instructions or SIMD instructions, like for example, these vector load, vector add, vector store, etc. And we have a vector length, which is the width or the length of our SIMD engines. And then in the SIMD model, SIMD execution model, we have multiple instruction streams or of scalar instructions. And these multiple execution instruction streams are the different threads. The hardware groups dynamically these threads into warp and executes the warps on the hardware. As you can expect, these warps have a certain length, right? Which is corresponds to the vector length, but here we talk about number of threads that compose the warps. In NVIDIA architecture, this value is typically 32. In other architectures, like for example, AMD, it's 64, and the term from is applied, so corresponds to AMD GPUs, while warp is a NVIDIA terminology. So there are two major advantages of SymT. The first one is that we can treat each thread separately. Recall that as a programmer, as programmers, we only need to worry about writing code for each thread independently. And there is an additional advantage, or at least potential advantage, which is the ability of creating warps in a flexible and dynamic manner. We will first talk about the first advantage. We'll later talk about the second advantage. But before we continue, I would like to take a break. Let's take a 10-minute break. I think that should be fine. And from here, we will continue talking about GPUs. Okay. So then I think that we can continue. We were here, this slide, where we are going to start talking about fine-grained multi-threading of warps. I think I have to apologize because I just heard that there were some audio problems in the previous part of the lecture. I hope that still most of it was understandable. You know that this recording is going to be available in YouTube, so hopefully you will be able to understand it, even if you need to watch some parts of the presentation a couple of times. And for sure, feel free to reach me if you need to clarify anything after the lecture, and also continue using Piazza as you are doing. Okay, so yeah, this is where we are, fine-grained multi-threading of warps. We are now going to talk about the ability of GPUs of executing warps and instructions for the warps in a fine-grained multi-threaded manner. We already know that GPUs are internally SIMD engines. We have seen in the previous slides that we program these SIMD engines in a more flexible and simpler manner than the traditional way of programming SIMD engines, which is using vector instructions. We can use threads, we can use the single program, multiple data programming model. And now we are going to see more in detail how these threads, when they are grouped into warps, are executed onto the hardware. So first of all, we know that, or we assume from now on, that a warp consists of 32 threads. So for example, if you need to process, recall this vector addition code that we are using as a running example throughout the previous lecture and this lecture, imagine that this N is 32K iterations. So, and we assign 1 iteration per thread. This means that we are going to need 1K warps, 1024 warps. And we probably don't have in our GPU SIMD units to execute all these warps at the same time. So that's why our SIMD units are going to be pipeline, and on this pipeline, we are going to execute these warps or the instructions from these warps in an interleaved manner. This is what we call the fine-grained multi-threading of warps. So recall our first instruction was the load different loads from array A in different iterations of the loop. We assign each of these iterations to a different thread, and then when these threads go to the hardware or are executed on the hardware, they are grouped into a warp, and essentially this warp is representing one vector instruction that is stored at a certain PC in the instruction memory, right? So the way that we launch the instructions for these warps is in an interleaved manner, as I said before. We can interleave the execution of instructions coming from different warps. And here you have an example. At this time in the execution, we launch or we issue this load instruction for warp 0, and then we may issue this loading, the same load instruction for warp 1, and then maybe this add instruction for a completely different warp 20 in this case. The way that we are able to do this onto the SIMD pipeline is by using a scheduler. This scheduler is responsible for taking each warp and deciding what instruction from which warp is going to run onto the SIMD pipeline at a certain time. Let's start taking a closer look at this SIMD pipeline of GPUs. This is pictorial representation of a SIMD pipeline, and as you can see on the top, what we see are like the architectural registers, like PC and mask, because recall this is SIMD execution, so we are also going to have a mask to handle things like branch divergence, as we will see in a few slides. And we have many of these, several of these. Well, in particular, in current GPUs, for example, we have 64 of these, if I recall correctly. So each of these corresponds to one warp. So this PC will be pointing to the particular instruction, next instruction that we are going to execute for warp 0, for warp 1, and so on. And when the scheduler decides to execute an instruction for a particular warp, we will have to go to the instruction cache, read the instruction, decode it, and then issue it onto the SIMD execution that, as you can see, is composed by several of these scalar pipelines that are what we have called SIMD lanes in some previous slides. There are a few of these cores, SIMD cores. We typically call them shader cores or also GPU cores inside the whole GPU. And these different shader or GPU cores can access memory through an interconnection memory and the corresponding and different memory controllers. So as we said, instructions from different warps are executed in a fine-grained multi-threaded manner onto the pipeline. You have a little bit more detailed pipeline here, the instruction fetch, decode, then we go to the register file for each of these lanes. We have the corresponding part of the register file, the part that corresponds to the thread that is going to run on this lane, and then ALUs, and at some point we will also have to access data from memory. We have a data cache. We actually have two types of caches inside each of the GPU cores. One of the cache is like a conventional cache, similar to the ones that we are going to see in later lectures, that is handled automatically by the hardware in a completely transparent manner with respect to the programmer. The other part of the cache is what is called a scratch pad, and this is also called kind of software cache, which means that the programmer himself or herself can decide what's going to be written into this cache for faster access. Because when we have caches in the pipeline, this means that their access is much faster than going to the large DRAM memory that we have outside of the chip. But yeah, so this is where the problem comes, right? Sometimes we won't find the data inside the cache, so we have to go to this GPU memory or GPU DRAM memory, which is typically called global memory in the GPU programming model. The problem with going to the global memory is that this takes even hundreds of cycles, right? But the way that we have to hide these high latencies of accessing data that resides in the global memory is by taking advantage of the fine-grained multi-threading execution. So while, for example, there is a miss in this cache, so we have to go to the global memory for warp 1 or warp 2 or warp 6, we can use the pipeline in the meantime to execute instructions from other warps that are not stalled because they don't need to go to the global memory yet. So this is what we call the ability to hide the latency, the long latency operations or the latency tolerance. And this typically works well for the type of applications that we are going to execute, typically regular, massively parallel programs that we are going to execute onto the GPU hardware. Like, for example, when we are processing images, images are composed by thousands or millions of pixels, and some of these pixels will be assigned to different, or these pixels will be assigned to different warps. And when we start executing operations for these warps, if it turns out that for a particular warp, let's say warp 0, we have to go to the global memory and bring some data, we can execute instructions in the pipeline for these pixels using other warps. Okay, recall also this slide, how the warp execution happens inside the SIMD unit, inside the GPU core, in a similar way as we have seen in SIMD processors. Depending on what's the number of lanes that we have inside the GPU core, we will be able to exploit more or less concurrency, more or less parallelism here. And again, you have just seen a GPU core, and essentially a GPU core is the same thing that you have here. It's composed by SIMD functional units, and each of these is divided into multiple lanes, and these lanes have different execution units that can read operands from registers. In this case, these are not vector registers. Here we talk about the registers that correspond to a particular thread, and each thread is identified by an ID. For example, here we have the registers from for register for thread 0, 4, 8, and so on. And also, you know, this slide as well, we were using it to explain the execution of vector instructions on a SIMD pipeline with a number of lanes that is smaller than the vector length. Here we do exactly the same for the warps. Now our vector length is the warp size, which is 32 threads. And in this particular example, we consider that inside each of the GPU cores, we only have 8 lanes. So if we want to execute the 32 threads of the warp, we will need 4 cycles to issue this load instruction, or this multiply instruction, or this addition instruction. But in the end, it's exactly the same idea. And if you think about this, there is even some sort of rigidness here. Why is that? Because warps are only 32 threads, right? We cannot change the warp size. It might turn out that for some particular problem, I may want to use more than 32 threads per warp, because, for example, I want them to run together and at some point communicate because they are executing together. If we want to do that, we can do it. And actually the programming model allows us to do so. Imagine this example here. We have, let's think that we have warps, not 32, but for this simple example is warps of 4 threads. So if we want to process these 16 data elements that we have here, we are assigning one of these data elements to one individual thread. And then when these threads go to execute onto the hardware, they will be grouped into 4 warps of 4 threads each, and then they are executed. The thing is, at some point, I may want these 4 threads run more or less together and more or less at the same time for the specific needs of my program. And this is always 4 in this example, or 32 in real world GPUs. So what the programming does is hiding the concept of warps to the programmer. These warps are not really exposed to the GPU programmers. However, what the programming model exposes is some similar organization that is called the block in the CUDA programming model, or is called the Wafer in the OpenCL programming model. And from the programming perspective, what we do is grouping the whole bunch of threads that we want to run on the GPU into different blocks of threads. And the good thing here is that the size of the block is something tunable. We can, the programmers can decide whether we want to use blocks of 100 threads or blocks of 200 threads. Actually, it's very typical that the size of the blocks is a multiple of 32 because, as you can guess now, when these blocks go to the hardware, will be decomposed into multiple warps of 32 threads. How do we execute a program on the GPU? We will typically have, recall Amdahl's law, sequential or serial parts in our code, and we will have massively parallel parts in our code. So the serial parts are going to run on the CPU that we call the host CPU. The parallel parts are going to run on the parallel device, which is the GPU. This is a typical CUDA syntax when we want to launch a kernel or a function. The function that we execute on the GPU is called the kernel. And here in this syntax, we define, in this call, we define the number of blocks that we want to launch and the number of threads per block. And then we will have the kernel will finish, this computation finishes on the GPU, and then we have some more serial code, and then we may launch another kernel, for example, kernel B. Very, very quickly, even though this is not the main topic of this particular lecture, we want to take a very quick look at how do we need to write code. In particular, this is CUDA code for NVIDIA GPUs to express in SPMD manner, in a multi-threaded manner, this sequential code or vector addition. So notice that this is the definition of the kernel. The kernel name is kernel function. And here inside the kernel, we are using a thread ID. The way that we calculate this thread ID is by taking into consideration the thread ID inside each block, the block ID among all the blocks that we are launching on the GPU, and the block dimension. This way we calculate this ID. We are essentially assigning one element of A and one element of B to each thread. We load these elements from memory into some temporary variables. We add these temporary variables and store the result in C. And here you have more or less the same code. Now it's a little bit more complex because we are doing some bound checking in this case. This n, for example, may not be a multiple of the block size. Maybe this n is 1000 and we are launching here 32 blocks of 32 threads, right? So in total, we have 1024 threads, and that's why we need to do this bound checking. So again, we calculate the indices, thread ID. In this case, we are using blocks of 2 dimensions, and here you see how we call the expression to call the kernel from the CPU code. This is CPU code. This is GPU code inside the same parallel program with also some serial parts, of course, as you can see. So if you want to learn more about GPU programming, you can watch this lecture. It's completely optional. We will link it from the course website, and it's it's an introduction to GPU programming from a previous edition of this course. Okay, how do we program GPUs? We use blocks, but obviously the hardware itself doesn't really understand blocks. The hardware understands the warps. So what we need to explain now is how we convert these blocks into warps. And this is actually pretty simple. Essentially, when we launch a kernel using a certain number of blocks of a certain number of threads onto a GPU, the first thing that the GPU does is taking each of these blocks and dividing them into warps of 32 threads. And now when they run, when instructions run on the GPU core, here you have an example GPU core from the Fermi architecture from 2010. When these warps of threads run on this GPU core, they run individually from each other. So when we launch an instruction, it's an instruction for one warp that belongs from the software side or from the software perspective to a certain block. So as you see, from the programmer's perspective, we don't need to understand what's a warp. We can use blocks. The size of these blocks is flexible. It's the hardware, the responsible one for dividing the blocks into warps and executing the instructions for these warps. Of course, if you really want to be a good programmer and write optimized code, you will have to understand what you have inside the GPU, right? So being conscious of the concept of the warp and the way that warps are executed onto the SIMD or GPU pipeline, it's important to get the most from our programs when executing on the GPU. Let's very quickly take a closer look at this streaming multiprocessor. This is NVIDIA terminology, or GPU core. Inside the GPU core, we have an instruction cache. In this case, we have 2 warp schedulers, which means that each of these can check what are the available warps that can execute instructions because their operands are ready, and launches or dispatches the instructions on these SIMD functional units. In particular, you see 16 of these SPs, which are just vector lanes. So we have 16 here, another 16 here, and these we also have some more that are, let's say, more specialized. For example, these are for load and store operations, and these SFU, meaning special function units, are execution units for some more specialized operations, like, for example, trigonometric functions like sine, cosine, and so on. As you can see, we also have the register file. We need to read the operands from there. And we also have some on-chip caches, a constant cache to store constant values. And this space here, I mentioned it before, is like the whole cache that can be divided into a, let's say, hardware managed cache and software managed cache, or scratchpad memory, which is called this shared memory in NVIDIA GPUs. Okay, so let's recap on warp-based SIMD and compare it to traditional SIMD. In traditional SIMD, recall we have a single thread. This thread executes sequentially, but it can execute SIMD instructions. These SIMD instructions operate in lockstep. We say lockstep because they, so it's like whole SIMD instruction, and then the next SIMD instruction, and then the next SIMD instruction for all the vector lanes. At the same time, the SIMD programming model is SIMD. We are not using extra threads. There is a single thread using SIMD instructions. And while in the warp-based SIMD, we are using multiple scalar threads. As I said before, it's easier from the programmer's perspective. We don't have to worry about the lockstep execution. We don't have to worry about packing different operands in the right way in using vector registers. The hardware is going to do that for us. The programming model is not SIMD, and we can play with the vector length in some way, because we can define what's the length of the thread blocks, right, or work groups in OpenCL. This enables to decompose these blocks into groups of threads, which are the warps, and then executed in a multi-threaded manner. The ISA is a scalar in this case. We are not using vector instructions, and essentially what we are doing is implementing the SPMD programming model on SIMD hardware. Recall that SPMD is a programming model. It's not a computer organization. It means a single procedure or program multiple data. And we have multiple processing elements executing the same procedure, except operating on different data elements. At some point, we may want these different threads to synchronize, right? But because not in all cases we will have such a regular computation as, for example, in the vector addition, where we can have thread 0 working only on element 0 of A, element 0 of B, and element 0 of C, and then thread 1 working on element 1 and of A, B, and C, and so on. They are completely independent. But in some other cases, we may want to synchronize. Let me give you a very simple example of when we need a synchronization. Imagine that what we want to compute in parallel is the reduction of a whole array. The reduction means the whole sum of all the elements in the array. If you have a sequential machine, You have a conventional CPU. What you're going to do is just reading element 0, accumulate, reading element 1, accumulate, element 2, accumulate, and so on. And in the end, we will have the sum of all these elements, right? But you can see here that there is a lot of parallelism, especially because in the reduction and when we use in addition, we can take advantage of the commutative and associative properties of addition. So one thing that we could we would do is distributing the whole array into multiple threads. Let's imagine for the simplest case that we have thread 0 and thread 1, and thread 0 is going to reduce to sum all the elements of the first half of the array, thread 1, the remaining elements. At some point, in the beginning, they can operate independently, right? So thread 0 goes and adds element 0, 1, 2, 3 until the half of the array, and thread 1 does the same. They can work independently, but at some point we need them to synchronize. Why is that? Because we need to, for example, thread 1 communicate the partial result to thread 0, and then thread 0 add the two partial values and obtain the final result. So if now imagine that we are not talking about two threads, we are talking about two warps. So these warps are executing in an interleaved manner, and at some point we want to make sure that they both have finished with the partial sums. So in order to do so, we use a barrier, and this is like a synchronization command or synchronization instruction that we use at some point in our program, and warps will wait there until other warps reach to that point. So that's something that also the SPMD programming model offers, and the hardware will handle it transparently. So essentially, we have here multiple instruction streams executing on the same program. Each program or each thread is working on different data, and they can even execute different control paths, right? Because same thing, in the same way that we can have these threads operating on different data, and at some point, for example, synchronizing, they can also execute, for example, if-else statements, and maybe thread 0 goes to the if path while thread 1 goes through the else path, right? So this is also something that the hardware will handle by itself. And this is a behavior that we can find in many scientific applications. And that's why, because we can take advantage of the GPUs in this way, that's why GPUs are also so popular these days for many different types of applications, not only regular computations, like, for example, what we need for a matrix multiplication or for machine learning and neural networks, but also more complex programs that require more synchronization across different threads, like, for example, graph processing. Okay, again, SIMD, I think you already know this slide. SIMD is a sequential instruction stream executing SIMD instructions. SIMD is multiple instruction streams of scalar instructions. We know already that each thread can be treated separately. As a programmer, I only need to worry about writing code for one thread, and then I know that I have multiple threads running in parallel or supposedly in parallel. Then the hardware handles everything by using the warps and interleaving the execution of warps. Now let's also see what additional features we could have in GPUs, the ability of grouping warps or grouping threads into warps flexibly in order to maximize the efficiency and the utilization of the SIMD units and maximize the performance. But before going to these ideas or to these proposals, let me very briefly discuss how we need to execute, as I said, the example that I just gave, right? We have different threads, and some of the threads go through the else and through the if path, and some others go through the else path. Here you have even a more complex example with different conditions that are evaluated. Some threads will go, for example, thread 1 goes through code A, B, C, D, E, and G, and then thread 2 goes through this path, and thread 3 as well, and then thread 4 goes to this path. And these are 4 consecutive threads, so it's very likely they are going to be grouped together in the same warp and executed at the same time. How can the hardware handle this? How can the hardware handle the fact that each of these threads needs to go through a different path? different control flow path. We are going to start with a simpler example. In this case, we consider like the if-else example. We have path A, for example, if path B, for example, the else path. And how do we handle this divergence? Observe that when we start the execution, all threads in the warp are executing together. They go to the branch, they evaluate the branch condition, and then some of them will have to go through path A, some others through path B. So that's actually what we do, right? These particular threads, for example, this is thread 0, 2, 3, and 7, execute path A, the remaining threads execute path B. We can handle this for sure. And I think we are going to see it in the next slide. We can handle it using mask execution in the same way as we use masks in SIMD processors. It's a hardware mask. But there is a problem here. The problem is that, as you can see, the two paths are executed independently, and we need to repeat, let's say, the execution for all the threads, even though only some of them are active, through the whole path A and then through the whole path B. So even though it's possible to execute this divergent branch onto the GPU, it's not the most efficient thing, right? So that's why we usually try to find ways, either in software or in hardware, to optimize our codes and optimize our hardware in a way that we can save some of these cycles. We will see some examples. Yeah, this is like, yeah, exactly what I said before is like what we call in SIMD processors conditional, predicated, or masked execution. And you have seen already in the previous lecture what's a vector mask or what are the mask vector operations. Now, let's talk about how we can potentially optimize the execution of these warps that have divergence. Let's say we talk about intra-warp divergence. Let's see a couple of proposals as a way to optimize the execution of GPU programs onto the hardware. We assume that we have many threads, and we know that we can treat, when we are programming the code, we can treat threads in an independent manner. Some of them will be at the same PC, and they will be in the same warp. And at some point, we are going to be able to create warps dynamically, as we will see in the next slide. This is a way of reducing the divergence and improving an important metric, which is the SIMD utilization. We call SIMD utilization the fraction of SIMD lanes executing a useful operation. So if we go back to this example, we see that here the SIMD utilization is 100% because all threads are active, but here SIMD utilization is only 50% because only half of the threads are active in this particular path, right? So in the end, what we want to do is maximizing this SIMD utilization, because this is the way of improving the performance of our programs on the GPU. Okay, so let's take a look at a possible way of doing this dynamic warp formation. We start with very simple example. We have two warps. They are executing if-else statement. Some of the warps, some of the threads of the warp go through the else, some others go through the if, and here the same for another warp. The good thing is that it turns out that even though these are two different warps that are launched at different cycles, in principle, they are going to be launched at different cycles. The good thing is that this warp Y is only using lanes that are not occupied by threads in the other warp. So the idea here, the key idea here, is to merge these two warps and create a single warp Z from threads coming from different warps. Originally, we launched the instructions for this one warp Z at the same time, and we are increasing the SIMD utilization here. In some other cases, we can find, I don't know, something like this, where there are two threads that are overlapping because they are in the same lane. So in this case, we cannot merge, or we cannot merge all of them. But for example, then if we have a third warp, for example, here, we can also merge a little bit more, and where we had 3 instructions from 3 different warps, now we have 2. So by increasing the SIMD utilization. And let's take a look at the same example as we saw before. When we go to the branch, we evaluate this branch. Some of the threads go through path A, some others through path B, and then for another warp, this orange or pink that just showed up, we also execute the branch operation. Some of the threads go through path A, some others through path B, and here we can merge, as you can see, and create a single warp that contains threads originally coming from different warps. And yeah, this is just like a kind of timeline where you can see a more complex example with different paths of execution, different blocks of code, A, B, C, D, E, F, G, and different threads are going to be following different paths. In the baseline, we see some divergence at some point. For example, here in path B, some of them go through C, some others go through D, and so on. This takes some time. When we do the dynamic warp formation, we create new warps from scalar threads from other warps. And for example, here for this block of code C, we can merge these 2 and create a single warp from 2 threads coming from 2 different warps. Then for D, E, and so on. And in the end, we end up having more efficient execution and faster, which is the actual goal. Okay, we are going to see another example here. It's we will. So first, so before going to the next example of hardware optimization that we can apply on GPU cores, let's very quickly recap on what we have inside each of the GPU cores. The GPU core is composed by SIMD functional units, each of them with a certain number of ALUs or processing elements. We group these ALUs or these functional processing elements into what we call lanes, and on these lanes we are going to have different threads from different warps running in different cycles, right, in a pipeline manner. The operands are read from the register file. It's a partition register file where some of the registers are assigned to some of the threads and so on. We have seen in the previous slide that one good thing is that if we have, for example, thread 0 from warp 0 that is going to run here, and thread 1 from warp 1 that is going to run here, and you know, the whole warps are not, you know, 100% utilized, we can merge these, right? And we can have faster execution because we can dynamically, or at least potentially can dynamically create new warps that have a higher utilization and are more efficient in the end. However, we have seen that there are cases where 2 threads from different warps have to go to the same lane and then somehow they overlap, so we cannot do this merging, right? Why can't we do this merging? There is one example here, like for this piece of code B, this blue thread and this red thread overlap, so we cannot merge the 2 warps completely. Why is that? Why do we have this problem? And it's because we cannot so easily move one thread from here to another lane. So in principle, inside the GPU core, the threads are statically assigned to the lanes. So it's not that easy. It's not that easy to move threads flexibly across lanes. Could it be possible? Yeah, it may be possible. You may come up with your own ideas to make it possible. Like, for example, saving these registers for thread 0, for example, in some temporary storage and then copying them into this part of the partition register file, and this way we are somehow shifting the thread 0 from this lane to another lane, and maybe this is a way of creating more efficiently utilized warps. I don't know. This is kind of food for thought for you. Okay, now let's take a look at another example of how to optimize the GPU hardware. This is a paper from our group from Micro 2011, and here we are going to talk about relatively easy, simple and easy to understand, but very efficient solutions for two of the main problems for GPU underutilization. One of them is branch divergence. We have just seen it. We may have intra-warp divergence, and this makes that we cannot fully utilize the warps in our program. The other big issue inside the GPU are the long latency operations. For example, going frequently to the global memory, which is far away, hundreds, let's say 200, 300 of cycles away, to bring new data and net data and bring it to the caches inside the GPU core. So we are going to see two ways. We have talked about branch divergence just now, so you must understand what the issue here is in order for you to see clear example of why long latency operations are also a problem. Imagine that we have all warps computing over time. They are executing instructions in the pipeline. Here inside these blocks that says all warps compute, we will have instruction 0 for warp 0, instruction 0 for warp 1, and so on, maybe hundreds of instructions here. But at some point, all these warps that have been executed in a round-robin manner, the scheduler just goes, takes one new instruction for one warp, executes on the pipeline, then takes another instruction, and so on. At some point, all these warps need to go to memory to read more data to continue the processing, right? So the problem is that at some point they all will stall in the GPU pipeline, in the GPU core, and they all will have to go to memory for many cycles until they bring the data, and this way they can continue the execution in the pipeline. Okay, so let's first talk about how to deal with branch divergence. The key idea here is kind of similar to the idea of the dynamic warp formation that we have seen in the previous example. The main difference here is that instead of merging two different warps of 32 threads, as we did in the previous case, here what we are doing is proposing the usage of larger warps, like for example, warps composed by 128 threads instead of 32. So when they go to the decode stage, this large warp goes to the decode stage, we may have some of the threads going through if, some other threads going through else, and we may have, in principle, divergence, right? But the idea of using large warps allows us to create smaller subwarps that are going to be merged and executed all together. So imagine that, yeah, in this particular example, I think that here we have like 24, imagine in this toy example, or the large warp has 24 or 32 threads, but in reality, the number of lanes that we have in the GPU core is 4. So what we do is we take 4 of these threads that we know that are going to be active on the current path, and we put them together, creating a subwarp, and then we launch this subwarp for execution onto the GPU pipeline, the GPU core. And then for the next subwarp, in this case, we only have 3 active threads, but again, we are increasing the utilization much more than what we would have had if we had just executed the subwarps, like threads, the 4 threads that belong to the same row in this figure. So that would be, as you see, the key idea is quite similar to the idea of the dynamic warp formation. It's another way of implementing it. And now that let's take a look at the how to mitigate long latency operations. Recall from the 2 slides ago that the problem is the fact that we have to go to the global memory. This takes a long latency. At some point, all warps need to go to the global memory in order for them to be able to continue computing. Here, the idea is to perform what is called a 2-level round-robin scheduling, where we divide the warps into groups of warps, and we schedule in a way that we first schedule all warps from one group, then we schedule all warps from another group. And this way, as soon as all these warps from group 0 reach this point where they need to go to the global memory, we can continue executing instructions from warps belonging to group 1, and this way we achieve more overlap. As you can see here, we are hiding the latency, this latency of the access to the global memory with the execution of warps on the GPU pipeline. And then we continue with the memory access for warps in group 2, and then we can also have some more overlap this compute with this access to memory. So this is, as I said, I would recommend you to read this paper if you are interested in this kind of techniques. Another way of continue, improving the GPU hardware and make it more efficient to increase what is called the SIMD utilization. Okay, so we are almost done with today's lecture. Now, this is more or less optional material. You don't need to watch it now. You can watch it later if you're interested. We are going to talk about the evolution of GPUs, in particular, a couple of 3 NVIDIA GPUs. And we are going to learn a little bit more about some of the execution units that these GPUs have inside. The very first example is this NVIDIA GeForce GTX 285. This is a GPU that was launched in 2009, and it's actually like relatively advanced in its family of GPUs. The first ones with this architecture were released 1 or 1.5 years earlier, and by that time, this GTX 285 was really powerful, including 240 stream processors. This is NVIDIA terminology. In the generic speak, we can talk about 30 GPU cores or 30 shader cores, as we also refer to them. And each of these cores contains 8 SIMD functional units, 8 lanes inside each of the GPU cores. We can take a look inside each of these cores. So this gray thing here is a whole core. Inside the core, we have the SIMD functional units. You can see that we have 1, 2, 3, 4, 5 until 8. And inside each of the functional units, so these are the lanes, what we have called lanes over the course of the lecture, we have also several execution units, like for example, execution units for multiplication or execution units for multiplication and addition in a single cycle. And then there are like more components here, like instruction stream decode is like the decode unit, and then some execution context, which is like PC, mask, registers, etc. You already know these details. Groups of 32 threads are a warp, and we can have up to 32 warps. By that time, we would have up to 32 warps running concurrently on each of these GTX 285 cores. So up to 1024 threads, or 32 warps of 32 threads. And this is a view of the whole GPU with its 30 cores and up to, well, more than 30,000 threads, as you can see. But obviously, since 2009, GPUs have evolved a lot. It's been like 12 years. And in 12 years, you can see how the number of functional units or stream processors has increased from how many? 240 in the GTX 285 up to we are talking about several thousands. I think it's more than 6,000 in the most recent A100 that was launched last year. not only the number of functional units has increased, also the computing performance that these have in gigaflops has increased, as you can see, at a very similar pace. And they are not only much faster, but also they are more energy efficient, because many of the innovations that have been applied onto the hardware over these years have had the goal of increasing the energy efficiency of these processors. This is another example. This one is from 2017. It's like, let's say, like the previous penultimate generation. Is a Volta V100. It has 5,120 of these stream processors. In generic speak, this is 80 cores, 80 GPU cores, and 64 units inside each core. We have it here because one interesting thing of this GPU is that it includes a new type of cores that are called the tensor cores and are specialized for machine learning. We are going to briefly talk about them. But first, let's take a look at the block diagram of the whole GPU. As you can see, 80 cores on the V100. One core is each of these that you can see here. They are labeled as SM. And they all have access to a relatively large L2 cache, the sizes and memory, large cache memory inside the GPU die. This size of the cache, if I recall correctly, is about 6 megabytes. And then the cores can access the external memory, which is the global memory, DRAM. Typically, in this case, is HBM2 memory, which is a special DRAM that is built by using different layers of DRAM and connected in a special way using a lot of lines from the stack of memory to the GPU in this case, and this way we can extract much more bandwidth. You will talk about, you will learn about memories in later lectures. Now let's take a quick look at the V100 SM or GPU core. As you can see, it's divided into kind of 4 main parts. In each, it's like a small GPU core inside a larger GPU core, right? So each of these parts contains its own warp scheduler to select the instruction from the warp that is going to be issued onto the pipeline next. We have this dispatch unit, we have the register file, and then we have these different execution units specialized for floating point 64 operations, so what we call the double data type, integer, float data type, and also we have these tensor cores that are the cores that I mentioned before, specialized for machine learning or deep learning. Because the main operation in machine learning is multiply, accumulate, and as you know, and Professor Mutlu explained in the systolic array lecture, it's possible to transform a convolution, for example, convolutional layer into a matrix multiplication. What the innovation here is to include in the core this type of smaller functional units that can execute this matrix multiplication in a very fast manner. So what they essentially do is taking 2 operands represented in floating point, 16 bits, they perform a multiplication, and and then they accumulate using another with some value coming from the accumulator, and they store again the result in the accumulator. And this is a way of, doing so. So what we can do using these tensor cores is dividing the whole matrix multiplication into small tiles, and each of these tiles are assigned to different tensor cores, and this way we can do this matrix multiplication much faster. We can even take a look at what we have inside the tensor cores. This is kind of a model that has been proposed by this paper from 2 years ago. In reality, we are not 100% sure that this is the way that the tensor core is built internally, but the authors of this paper, what they did was doing a lot of micro benchmarking and reverse engineering in order to understand how these tensor cores work and propose a possible microarchitecture for these tensor cores. What we know from this paper is that each warp utilizes 2 tensor cores every time that we need to execute instructions for one warp on the tensor cores, and each tensor core is divided into 2 octets. And now if we take a closer look at each octet, we see that it also has like kind of 2 thread groups, and in each thread group there are SIMD execution units. In particular, one SIMD execution unit is what you can see here that performs a dot product operation. Several operands are fed here. Then we have multipliers, then we have kind of parallel tree reduction, and we obtain some value that is stored in the accumulator. So with these tensor cores, we can perform a 4x4 matrix multiply accumulate in one cycle per tensor core. So this is why they are so fast at executing matrix multiplication and consequently machine learning workloads. There is something interesting here as well, because even though you can see this is kind of a SIMD unit as well, it's kind of a specialized SIMD unit that we also have inside the each GPU core, but there is some interesting thing that makes it different from the conventional SIMD units and even from the other SIMD units in the GPU core, and it's the fact that now for these SIMD units, it's possible for some of the threads, for example, here we have lanes 0 to 3, it's possible for them to access data that is stored in registers from other threads. And this is relatively special, as you can see. So the register contents are not anymore private to each individual thread, but now they are shared inside the warp when it comes to the execution on the tensor cores. And now we have the latest NVIDIA GPU here is the A100. It has even more of these stream processors, in total 108 cores with 64 units inside. The tensor cores are also there. They are now a little bit optimized. They even have support for sparse matrices, as we will see. And they also incorporate a new data type that is called tensor floating 32, I think. It's a data type optimized for machine learning and neural network training. And this is the overall view of the whole GPU. It's very similar, as you can see, to the B100. The main difference is that it has more cores. It can potentially have up to 128 cores. Another key difference is that the size of this L2 cache now it's much larger. In the previous generation, it was like 6 or 8 megabytes. Now we're talking about 40 megabytes. As you can imagine, this can be really beneficial for many workloads that can really take advantage of this larger cache. And now we also have the external access to the HBM2 stacks as well. And if we take a look at the tensor cores in this A100, what we see is that, well, they have this support for sparse matrix operations. It turns out that in neural networks, many times we have the weights that we use in each of the layers of the neural networks, but sometimes after training, some of these weights are 0 or they are almost 0. So what it means is that when we are doing inference, we don't really need to, it doesn't really make sense to perform multiplications by those 0 elements, right? Because we know already that the result will be 0. So what the tensor cores now can do is compressing these weights in a way that we are going to save a lot of space, and also we are going to be more efficient in the execution in the sparse tensor core, because we are not using the tensor cores to multiply something by 0, which is completely unproductive. So this is essentially the key idea here. Okay, so we are almost done. I hope that you have enjoyed the lecture. I hope that you have learned how SIMD processors work, how GPU works, how we program GPUs, the main difference between the key differences between the SPMD programming model and the execution model. SPMD as an example of programming model. Just a final slide, some food for thought. You have seen that GPUs are highly optimized processors. They are especially optimized these days for execution of machine learning workloads, neural networks, and so on. And we also know that another type of processors that are also specialized in this type of workloads are systolic arrays, like, for example, TPUs that Professor Mutlu explained in the systolic arrays lecture. Is it possible to get the most of both worlds and combine them? It's something for you to think about. Would it be possible to maybe embed small systolic arrays inside the GPU, or maybe make the systolic arrays more general purpose to have, let's say, more flexibility when it comes to executing other types of workloads different from matrix multiplication or this kind of regular computation? This is something that you can think by yourself. And also try to answer these questions. We are already discussing about them, which one is better for machine learning or for image video processing, what type of parallelism each one exploits, right? So on the one side, we have GPUs with SIMD execution units and using also multi-threaded execution. On the other side, we have TPUs that are systolic arrays. What are the trade-offs of each one, and so on. So if you are curious about these, the answer to these questions or potential answers to these questions, I would really encourage you to take other courses from Professor Mutlu, like, for example, the bachelor seminars in computer architecture, where we discuss different papers from computer architecture, relevant, very important papers, some of them more recent, some of them even decades old. We discuss them, and it's a way of approaching to important topics in computer architecture. And of course, you can also take the computer architecture master's course that Professor Mutlu gives every semester, every fall semester. Okay, and I think that this is all from my side. It took like 7 more minutes, but as you know, the last part of the presentation is completely optional. I hope that most of the questions that you have asked on the chat have been solved by other TAs. We will review all these questions, and as you know, we normally do, we will post them in Piazza for your reference. If you have specific questions or ideas that you would like to discuss about GPUs, please contact me, contact Professor Mutlu or other TAs, and we will be glad to discuss with you. Thank you very much. Have a nice evening, and see you in the next lecture.